Welcome to the first video in our Class 4 series of lecture videos. Today we'll be discussing stereochemistry of the diene and alkene in Diels-Alder's reactions. And as you can see, the very first point is the stereochemistry of the diene and alkene is always maintained. What do we mean by that? Well, let's take a look at this example of 1,3-butadiene reacting with this alkene called cis-dimethyl malleate. So it's got a couple of methyl ester groups on our dienophyl alkene, and they are cis. That means they're on the same side of the alkene, just as the hydrogens are on the same side, and that shows up in the product. We note that the two methyl esters are cis groups on this cyclohexene ring after our 4+2 addition. There's one stereoisomer. It's got two stereocenters, so we would call this meso because it's achiral. There's an internal plane of symmetry. We'll discuss more about how we end up with certain stereochemistries in this, and it's quite something. Once you see it, you can never unsee it in terms of having an aha moment. And like I said, it's really kind of an interesting section of the chemistry that we're venturing upon at this point. So because the reaction is concerted, the two hydrogen atoms end up on the same side of the cyclohexene product, and obviously the two methyl ester groups ended up on the same side as well. How about if we did the reaction of 1,3-butadiene with trans-dimethyl fumarate? Now this is a, believe it or not, billion-dollar blockbuster multiple sclerosis MS drug at this point. It wasn't when I wrote these notes, but it's amazing how things change. In this case, we end up with the trans cyclohexene products, so our methyl ester groups end up trans to each other. And we don't only end up with this particular stereoisomer, we end up with an equal amount of its non-superimposable mirror image, which we would otherwise know as its enantiomer. So it's racemic, and like I said, what that really means is there is an equal amount of this non-superimposable mirror image in the product mixture. Like I said, as we encounter more examples, we might have a better feel for how the stereochemistry develops. One particular good example that we could use concerns when both the diene and the alkene have groups on them. And so what am I doing here? I am trying to be tricky and show, okay, well, what happens when both the diene and alkene have substituents? We start off with something called cyclopentadiene. So this particular diene has, a conjugated pair of alkenes, except they're in a 5-membered ring, and it looks like we're using this cis-dimethyl malleate, and we're doing the 4+2 addition. So a transition state that you might think about is here we have our alkene coming under the plane of our cyclopentadiene, and we're going to be forming bonds. And what are the bonds we're going to be forming? They are these dashed lines, right? You can still see the alkene intact. Here are the dashed lines, right? And here are the two alkenes, the two pi bonds of our cyclopentadiene, right? Our 5-membered ring. And what have I done? I've pushed that, bridging carbon, I've pushed it up instead of leaving it in the plane. So as these bonds form, that 2-carbon bridge gets kind of pushed up. Now this is one possible transition state, and the way that I originally drew it in your notes was to have dashed lines go all the way around. In other words, what I'm trying to represent is in the transition state, we're breaking this alkene, we're breaking these alkenes, right? We're forming these carbon-carbon single bonds, and we end up forming an alkene back here. So yeah, that's how I had represented it in the notes, but I overlaid that transition state, which had the alkene intact and the diene intact, showing you how they sort of plug in together. But you could think about those electrons as being delocalized around here, right? Because obviously we're breaking that double bond, we're breaking these pi bonds, we're going to form a 6-membered ring and a cyclohexene, right, an alkene at the back where there had not been one before. So moving forward, once those carbon-carbon single bonds are formed, we've got this 1-carbon bridge, and lo and behold, from the transition state that we showed, where the hydrogens were under the plane of our cyclopentadiene 5-membered ring, we get this particular stereoisomer. We call it the exo product, and it's meso, right? It's achiral. It has stereocenters, but there's an internal plane of symmetry that cuts through the molecule. We call it the exo product because the methyl ester groups are said to be exo or cis to the smaller bridge that has formed in our product. It's just a kind of strange way of designating this particular product. And there's a very unintuitive aspect to this reaction. So of course, if we considered a transition state where the hydrogen atoms were underneath the plane of the cyclopentadiene ring, we have to consider another potential transition state. So what about another possibility? And in this possibility, and this really takes your three-dimensional, visualizing capabilities, it kind of maxes them out, right? But you can see that in this particular depiction, we have our alkene coming in to plug into our conjugated diene, right, and form carbon-carbon single bonds. But now the methyl esters, the CO2-MEs, are underneath the plane of that 5-membered ring, right? And the hydrogens are sort of pointing out away from it. And of course, this 1-carbon bridge gets pushed up. So here we have our transition state, right? Where we're going to be breaking the alkene, forming these, carbon-carbon single bonds, and then forming an alkene back here as we break the 2 pi bonds in our cyclopentadiene. So what's unintuitive about this is we think, oh, well, sterics, we had seen in the first semester of organic chemistry, was a major determining factor in whether reactions went or not. And we have this intuitive sense that these methyl ester groups, these CO2-MEs, are much bigger than hydrogens. So maybe sterically they would be bad to put underneath this cyclopentadienyl ring, right? Because maybe they would interfere sterically, and there would be some sort of repulsive interaction between those groups and the cyclopentadienyl ring, versus having a hydrogen underneath that ring, because hydrogen's pretty small. It's as small as it gets atom-wise. Anyways, this is referred to as the endo product, and we can see after we've unfolded it that these 2 CO2-Me methyl ester groups are pointing straight down. The hydrogens are cis on the same side with that smaller carbon bridge. So like I said, the methyl ester groups are said to be endo, or the hydrogens are cis to the smaller 1-carbon bridge, but the methyl ester groups are trans to that 1-carbon bridge. And yeah, Endo Rule. All right, so what's the punchline for this? The non-intuitive thing is that of those 2 transition states, so strange as it may seem, the endo product is actually favored. And what that means is the activation energy for that endo transition state corresponding to that double cross 2 transition state that I drew, is lower than the activation energy corresponding to the exo transition state, the first transition state that we encountered in notes. Why? Why is it lower? Why is that activation energy lower? We thought, oh, sterically, it should be repulsive. Well, it turns out that that activation energy is lower for the endo case than the exo case because there is something called secondary orbital overlap. So there are pi bonds in that those methyl ester groups, right? And they actually overlap with the diene's molecular orbitals. So that pi system of the methyl ester overlaps with some of the diene's molecular orbitals. And that has the effect of lowering the transition state for having that endo configuration versus the exo. And if that endo configuration transition state is lower, well, the reaction goes faster. And that's why we end up with more endo product than exo product. And so we've come to call it the Endo Rule. So we like to put groups that have pi bonds and that are electron withdrawing, we like to put those such that they're oriented, under the plane of the diene. It could be above the plane of the diene, depending on how you look at things. In the particular case we showed, it would not matter whether you reacted that alkene under the plane of the diene or over the plane of the diene, you would get the same product. In some cases it does matter. You get a one enantiomer versus another enantiomer. So it's something that we'll definitely practice, and hopefully it's something that you will, come to easily grasp and see when you encounter various Diels-Alder reaction problems. All right, well, with that, we'll pick up on a summary of the relative stereochemistry for the Diels-Alder reaction in our next video.